About 10 years ago, I started my career as a software engineer. I took a job contracting with an ad tech firm, and we were solving problems that are very typical of anyone who's worked in ad tech before. We had ad impressions all over the internet, put up ads, get people to click things, capture clicks all across different web properties, and do the holy grail of ad tech, figure out who clicked the ads. And that's a super important problem because of money. People click ads, people make money. There's a very big market around this. And so this was very exciting to work on. It's like one of my first jobs out of college. And it kind of started my foray into streaming. It was one of the things that got me really excited about this. And so 2014, things were different. We didn't have as many things in the cloud, didn't have as much tech as we do right now. But you can imagine ad impressions. We show an ad to you. It's a very obvious event that belongs in a Kafka topic. Clicks, obviously, very clear event stream. So put these both in Kafka topics. And then what we wanted to do was take all of the ads that actually got clicked and figure out who got paid out, put them into MongoDB, and then we could do things like analytics, run a web service on top of it, do all kinds of different things. And so the architecture kind of looked like this. We had ad impressions on the left and clicks on the left as well, and then our sort of gold data set on the right of clicked ads. And in the middle, 2014, we had Apache Storm, which, if you're not familiar, is kind of like Flank's uncle, the predecessor to all the good stream processing that we have right now. Really the first, mainstream stream processor. And so, yeah, again, 2014, very little of this was in the cloud, and so we ran all of this in like AWS, I think, all on just a bunch of VMs. And so it wasn't a huge volume of data, but it was definitely like a lot for the time. I think it was in the order of like thousands or tens of thousands of messages a second. And so running multiple brokers of Kafka, multiple shards of MongoDB, definitely more than it's not a trickle of data, but also not Google scaled. So somewhere in the middle. And so getting ready to go, getting ready to basically go ahead and deploy this. Everything's looking good. We go ahead and get the code written for this. We kind of work with the business folks to figure out what constitutes somebody getting paid out. This is some Clojure code. It roughly resembles what we actually did for this project. And the strategy was pretty simple. We would do kind of a processing function on the fly. We would connect to MongoDB. Every time we got a clicked ad, we would go ahead and put that in document database. To back up for a second, every time we get an ad impression, we put that in a document database. Every time we get a click, we'd also put that in. And then we kind of do a lookup of the two, see if they paired up, and then put that in a separate collection so we could do a window of figuring out who's clicking what and basically get people paid. And so the logic wasn't terribly complex. There were all kinds of hitches you can imagine with what constitutes a click that matters. But the code was pretty simple. The tests were pretty simple as well. We basically mocked MongoDB. We kind of figured out, does our business logic actually work from like a unit testing perspective? And so just kind of wrapping around, figuring out, do we call the database at the right time? Do we get the right value when we query the collection? All looks good. So getting ready to deploy, the tests pass, the deployment succeeds, the alerts are firing, monitoring seems to be working. Here we go, launch day, and like immediately everything is on fire, and we have no idea why, right? And so we do a lengthy post-mortem, go around from component to component trying to figure out, is like this Kafka, is this Storm, is this Mongo? Turns out it was Mongo, but not really because of like MongoDB's fault. We were actually dramatically undersized for the workload that we were doing. And if you've worked in stream processing before or ad tech before, you'll kind of see why from that pseudocode that I showed you. The approach that we took was actually quite silly. We were basically like every event that we got hitting the database multiple times, which is hugely inefficient. So we just like a 3-shard Mongo cluster really can't keep up with that quite fairly because it's not really a great strategy for doing this. And so get on the phone with MongoDB, figure out, okay, we need to size up Mongo. We need to get back in production. Let's get going. So we size up Mongo. The tests are good again. The deployment's looking good. Everything's fine. Now we do the same architecture diagram, just with more Mongo. Looks more impressive. And so we go ahead and we launch. Everything looks okay. Everything's going fine through the week. We get to the weekend. Everything's going really well. And then everything is on fire again on Saturday night. And what happened? We don't really know. We're going back to the post-mortem process. First people we call our MongoDB because that was the problem last time. And actually, sure enough, now we're suffering from something different. We're suffering from a hotkey problem now. Now we're properly sized. But if you're not familiar, a hotkey problem is when you run multiple shards of your data, you effectively paralyze it. But the nature of your data is such that effectively all of your data just goes to one shard. So no longer do you run 9 shards in Mongo. It's like you're running one. And it was an artifact of the way that the data happened to look on the weekend. And we didn't know that because we'd never done this before. It was the first time it was in production. It was the first Saturday night. And so it's kind of unavoidable in a sense. And so things that went well to kind of like describe, what was this journey all about. The code review was good. We did unit tests. We made good tech choices for the time. Things that did not go well. We did not understand our production traffic, so we didn't have it yet. So it's just sort of like a catch-22. We didn't test with prod again for the same reasons. And then we didn't really understand the underlying tech. Like that join strategy that I just described is actually insane, and you wouldn't want to do that in practice. But we didn't know, because like the integration test passed and everything looked okay. So unfortunately, this is the end of that story for me. If you're junior in the crowd, you get to mess up pretty big on a major project once. You don't get to twice. So I don't have like further lessons learned on this one. But what I can tell you is that I'm 10 years older and 10 years wiser. My name is Michael. I'm very easy to find on the internet. I write a lot on LinkedIn. I write a Substack. Come find me. I love to chat with other engineers. And I spend my days now solving what I call the $10,000 demo problem, which is basically what it sounds like. You need to build a great demo or a great test or a great POC. And underlying in that, what you actually want to do is to do something that is representative of what your customers actually use your product for. And I think that's way harder to do than it sounds. Getting the right data for that is quite hard. And it's just reminiscent of kind of the story that I just described. If we had the right data to do these things, this wouldn't have been such a problem. But instead, we had many, many hours of support with MongoDB, a significantly sized up cluster that we didn't need. All of these things actually just build on their own complications. And so I think this is a very important problem to solve. I do think that if you're kind of going into these things, the first thing you want to do, to be like completely fair, is to use production data if you can to actually test your systems, to do demos, to do all these things. But there's a bunch of further caveats to this. Like number one, you may not actually be in production yet, which was the case for young Michael 10 years ago. We didn't have production data to do any of this. Number two, and more commonly, you may have PII everywhere. If you live in Europe, this is especially hardcore, and so you have to be careful with that. Number three, you may have firewalls everywhere. It's just purely inconvenient to use production data for testing or demo purposes or whatever, and it's just kind of hard. Some more future type things, you can't really model what may happen. So it's Wednesday, data looks good. What will happen on Saturday? You don't really know, and you need some basis for sort of adjusting for future scenarios. If you're in sales, the data may not actually be yours. This happens all the time. If you're working with a prospect, they can't readily give you their data to go run tests like this. And then lastly, I think this most importantly, you can't ask what if. Like if you're in retail and you're wondering what is going to happen on Black Friday when our production traffic triples, if you haven't experienced that yet, you don't know and you can't test for it, and you're basically gambling with something that's probably really important. And so the solution to this, I think, is synthetic data, or fake data is the real word. Synthetic data is the fancy word for it. But it's actually still kind of hard to do, right? Because your real data is not trivial. It's not like a string or an integer. It's probably a deeply nested schema that has all kinds of special semantics around it, and it's kind of hard to model. If you're using fake data, off-the-shelf things, they're kind of unrealistic. You can't just generate strings. They have to be real customer names or real addresses or real geospatial data or stuff like that. And so that's kind of hard too. If you have multiple data sets, as almost everyone in this room does, your data is not simple, it's correlated. It actually needs to be joinable across different data sets. And it's particularly tough with streaming. Like if you have customers and orders, they actually have to match up on a join key for any of your applications to actually function. Bad key distribution. If you just generate data at random, you're just going to get something fully uniform. You won't smoke out the kinds of scenarios that I described in my ad tech journey. Unusable sequencing. This is a very subtle problem. If you do something like parcel tracking, your events need to arrive in a specific order. You don't have an order that goes from delivered to shipped. It goes from processed to shipped to delivered, and you have to get that right for your applications to function. And then lastly, you want to actually mimic user speed. You don't want to just trickle out bytes. It's not really going to do anything. You actually want to run at the pace of production or scenarios that you find interesting and helpful for what you're doing. And so I spend my days building a product called ShadowTraffic. It is a product made to help simulate production traffic to Apache Kafka. It's a closed source project, but I wanted to come here and actually open up the design and just share some of the tools that I use to create a high-performance synthetic data generator. So you can take away some of these tools on your own projects, use them in ways that apply to you, and hopefully you find that helpful. And so what are the goals for writing a good synthetic data generator for streams specifically? They're kind of like the contrary goals to the contrary problems to what I had mentioned earlier. So we want the ability to quickly model nested deep data. It has to be realistic, even though it's synthetic. We want to have good relationships and correlation across multiple data sets. We want to be able to model stateful functions, so data that changes over time. Think like geospatial data. We actually want to have objects moving from point to point, and we don't want to have fully random data because that won't help you model your app. We want it to be fast, we want it to be repeatable, and then we want it to be composable. If you don't have these, you don't really have a tool that's going to be suitable for engineering. It's going to be just kind of a crapshoot every time. And so what I want to do is actually sort of work up to the sort of data that I introduced in my story. I want to be able to generate data that is relevant for ad impressions and clicks in such a way that it would have been useful for me in the past. And the API that we want to end up with is something that resembles ShadowTraffic. So it's a JSON DSL that you effectively, if I just kind of pan back and forth, we just rip out concrete values and we put in little maps that have _gen, which says, run code here. I think data DSLs are a fantastic way to model these kinds of things. They're very dynamic. And so this is sort of the goal that we want to work up to. We want to have the foundation to get to something like this. And so the rest of the talk, I'm going to take you through what I call like the pyramid of importance for synthetic data. You got to get the lower foundations right to do anything in the upper tiers really well. And yeah, we're going to get going. So I'll start with single-threaded code. So this is actually kind of funny because I just said we want to go really, really fast. This is important for load testing. This is important for predicting future speed. And so what's the deal with that? You think single-threaded code, you think slow. This is actually kind of counterintuitive. So what we want to do is we want to create an architecture for synthetic data that has a dichotomy. We want our data generation to be single-threaded and synchronous, and then we want the sending of the data to be fully asynchronous. And why? The reason is that if we want to actually attain kind of the other goals that I mentioned, deterministic randomness, deterministic time, anything that will let you have reproducibility, you have to have single-threaded code. Otherwise, you're going to have just effectively unpredictable code. You can't really make these things work well across multiple threads. We're very fortunate in this room. For anybody who's doing Kafka data production, multi-threaded asynchronicity is totally the client's problem. So when you call send on a record, it gives you a callback. It takes care of lingering and batching. This is really, really nice that you don't have to do this yourself. If you're using something like JDBC, you probably have to have like a fixed thread pool where you're maintaining that batching and that sending. There are good system calls these days with like Linux and IO Uring. So there are solutions here. But what we want to do is actually end up in an architecture where we have two pieces: synchronous data creation and then asynchronous data sending. And what I want to do for the rest of the talk is actually code through this and build it up in a simple way, kind of reverse engineer sort of the essential parts of ShadowTraffic so this doesn't be so theoretical, but instead moves to something that is practical and visible. And so here we go. I'm going to write a little. I'm going to evaluate a little bit of Clojure code. If you're not familiar, Clojure is a dynamic list for the JVM. The parentheses are just sort of on the other side, and so you could almost all intuit what this code is actually doing. But what I'm going to do, I have code over here. I'm in Emacs. I'm going to evaluate it. And I can do things like I could say 2 + 2. And what you'll see in my lower left-hand corner is the result of actually running this code. And that's much of what I'm going to do during this talk, is sort of evaluate and see the results as I go. And so the goal here is to sort of set up this dichotomy in the architecture, and I'm going to start very, very simply. I'm going to start with two functions that are just generate an ad impression and generate a click, and right now they are incredibly stupid. So I have my generate ad impression, I pick a random ad ID and I timestamp it with the current time, and then the same for clicks. I just pick a completely random ad ID. These are never going to correlate because UUIDs effectively never overlap with one another. I hard code a URL, I hard code a timestamp. This is just the bare minimum to get an architecture working. And then I have a function on top of that, which is to just generate data, give me a map to say what to do. I want to have some dispersion. I want to generate an ad and a click, an ad and a click. I actually want to have that round robin nature. And the easiest way to do that is to just keep track of what event number I've generated. If it's even, we'll do an ad. If it's odd, we'll do a click. And then I'm going to cheat a little bit just to keep the talk really simple. Instead of actually sending the data to Kafka, I'm just going to print it to standard out. But if I wasn't, I would just have something like this. Send to Kafka for real. I would just have a callback, and like I said before, we're very lucky that async IO is built into Kafka. So if I just slam send on the producer, it's going to take care of efficiently getting these things out the door, giving my callback back to me, and taking care of all the messiness of actually doing that in a very performant way. And then I'm going to bring this all together with a function called execute side effects. All it does is take the map that I had and generate data and sort of figures out, well, what do you want me to do? In this case, so far, we only have one action. We're just going to send the data, and so it's going to invoke my side effects. And then I have all the messiness of actually generating the data. So I'm just going to generate 5 rounds. It's going to go 0, 1, 2, 3, 4. Call generate data, execute side effects, recur, and away we go. And so nothing particularly surprising here. I'm just going to call generate 1. And I'll get a bunch of data. This is going to go back and forth. I get add impression, click, random UUIDs. None of these are ever matching. The timestamps are all reflective of the current wall clock time. The URLs are fixed. But what I do have is basically the basis for an architecture that's going to let me do deterministic operations and still be able to be fast on the Kafka side. So if I go back to my slides, I'm going to keep bumping my way up this pyramid and talk about semantically accurate data. So I just really hard-coded a bunch of stuff into my functions, which is fine to get started. But what I actually want is kind of a rich suite of data to work across whatever domain that you're in. And I just say that there are no secrets here. This is actually just work. Doing scalars is easy, like ints, booleans, bytes or whatever, that's fine. But where it matters is actually being able to support statistical distributions for your data. To say 80% of the time we do 20% of something and be able to kind of skew the population in that way. We want to be able to do geospatial data for when that matters. This is supposed to be Texas. Sorry, Texas. Yeah. We want to have good datetime operations. Everyone's data has, datetime semantics in it. Same with math operations, that comes up. Selection, the ability to sort of correlate data or weight it and say this often. So a certain percentage of the time something happens and a certain percentage of time something else happens. And so this is all just work of accruing data sets, cleaning them, indexing them, making them queryable. And I'll show you just a little bit. I wanted to keep it simple for this part of the talk. So I'll go back over to my editor, and I'm going to start to add a little bit more richness to the data in these add impressions and these clicks. And so I'll just wrap around, random UUID, say if when I want an ID, this is kind of where it comes from. And when I make a URL, what I have here is just sort of a set of random choices. I'm going to have some base URLs, example.com, my website, whatever. These are all lame and terrible, but for the person at the top, they're scoped tightly enough to get the point across. I'll have different paths. I'll sometimes have HTTPS and SSL, and sometimes not. Same with www, sometimes I'll leave that out. And I'll just randomize this to all put together, different URLs. So if I run random URL, I'll get example.com/services, random page, whatever. And this is like a little bit more rich. In practice, what you would want is a library like Faker or all kinds of projects out there that have just accreted a huge number of realistic strings, and you want to pull that into your project. There's like one of these for basically every programming language that's out there. Along similar lines, I want to randomize the timestamps. I don't want to have completely present wall clock time. I actually want to skew this a little bit into the past or into the future. So I take an offset of about 600 milliseconds, grab a random amount of time between 0 and 600, compute a sign, and then just say, well, the timestamp is actually not right now. It's like a little bit in the past or a little bit in the future. So that helps me model a little bit of latent data or early arriving data. And like I said, this is kind of all just work. This is a function that I ripped out of ShadowTraffic. There's a rich suite of geospatial data, and this is a function for heading. This is just like, if it matters for your domain, you actually just have to go put in the sweat to sort of figure out how do you replicate that. And so people find that kind of useful. And so I'm going to go ahead and update my data generation function. So I'm redefining what it means to generate an ad impression. And to, I've been so excited talking, I've actually forgot to evaluate all these functions as I talk. So I'll go ahead and redefine these functions. And now generating an ad impression, I generate a random ID as before and a random timestamp, and ditto with a click. Now I'm going to use my new random URL function. And like I said, if I evaluate that, I get slightly better data. And so now when I run this, I'm getting better URLs like you saw. So my website, random page, whatever. The timestamps, you can't see them yet, but they are a little bit askew from the current wall clock time. And so this is just the process of figuring out like what is important for your company and your domain and going and finding the right data for it. So the next thing I want to talk about is doing deterministic randomness. We want to actually be able to control the data that comes out. You want it to be predictably unpredictable, so that if there's a problem, you can kind of test it away and figure out how do I actually zero in on what's going on here. Deterministic randomness is kind of funny because it doesn't really make sense, sort of a paradox. And the way that it works for, again, basically every programming language, but this is just an example for Java, there's probably like a random class or object in your programming language of choice. And generally what you can do is you can create primitive data out of it. You could say, give me a random int, long, boolean, double bytes, whatever. And you won't be able to predict predict what comes next. That's sort of the whole basis for the class. But what you can do on almost all of these is pass it a random seed in the form of a number. And when you give it a number, it actually seeds the state of what's going on inside of it, so that when you call any of these functions, as long as you call them in the same order every time, you know exactly what is going to happen. So what's actually happening here is that your seed is sort of teeing up an initial state. And so when you call next int 3 times in a row, that internal state is advancing to known values. And so you can predict what this essentially random object is actually going to do. And again, it's very useful for testing reproducibility, really important to be able to manage this stuff. And so let's implement this in our code to make this a little bit more well-behaved. So I'm going to create a top-level object called random, and it's just an instance of Java util random. I mark it as dynamic so that I can go in and rebind it later. And then I'm going to override my synthetic data functions. So I have drand, which says give me a random double, drand int, which says give me a random int between any 2 numbers, and then drand nth, which says give me a collection and then take a deterministically random element out of it. So I could have stable access to arrays and vectors and things like that. And then it's not just primitives. You actually have to be careful with this as you go up the stack. So like there's no random UUID function that's stable. What you actually need to do is to use a deterministic random generator on the least significant bits and the most significant bits, and then construct that together. And so this is true of a lot of functions, but UUID is a common one. And it's kind of a tricky thing. Like if your architectures are complicated, you actually have to go into all of your libraries and make sure that all of them are using deterministic randomness. Otherwise, your program will not be well behaved. You'll get different sets of data on different runs, and it's a lot less useful to you. So I'll redefine my data generators. Random ID is now deterministic random UUID. Same with random URL. What I've done is I've subbed out rand_nth for drand_nth and drand int and so on and so forth. And now that will be deterministic. And then I've got random time, which again, I'm just going to use drand int and drand nth to get deterministic time off of the current timestamp. So now if I run this, what I actually want to do, instead of just well, actually, before I show that, what I want to show is this in the small. It's kind of a lot of information. If we look at kind of a smaller example, if I set the seed to 42, I bind random to use this deterministic random seed, and then I just create an array of a random floating point number, a random integer, a random UUID, and a random element. What I should get is the same result every time, and you see this in the lower left. I get 0.72 every single time, the same UUID, the symbol C comes up, and so you'd see this just in one function call. What we want this to do is to pervade the entire stack of every call. The same random functions being called in the same order every time will give us the same response. And so now if I do this across my larger generator, what I'll see is that these UUIDs are the same. So if I'm running this over and over, notice that that last add ID is always the same, C053. In event 3 there, you see the same URL, coolsite.net/products. This is incredibly useful for when you're testing. If you find a bad state, you can go grab the seed, you can rerun it, and it's much calmer to work on a complicated problem when you know you can reproduce things. And so to move up the chain a little bit, deterministic time is another related but different piece. There are all kinds of reasons that you would want to have deterministic time. For one, it actually makes idempotent tests significantly easier. If you wrote a test last month, you actually want it to behave the same as this month, which is particularly sensitive for streaming data where time matters, timeliness, late data, early data, things like that. It also helps you simulate windows of time. If you want to say, how will data look on Saturday, you don't want to have to do a bunch of gymnastics to actually change your timestamps on the fly. You actually just want to pass in a timestamp to say, hey, system, behave as if it's Saturday. And then additionally, if you do this really well, you have the basis for speeding up and slowing down time, which is really useful to be able to narrow in on particular problems that you'd observe at particular hours of the day. And so this is just another piece that's like just maintain sanity. Moving forward, I would build this into every single system that touches time. It's just kind of the right way to do it engineering-wise. I'll jump back over to my editor. And I'm going to go along a similar process. So I'm going to just do a few precision changes. I'm going to override my random time function, no longer to access the current wall clock time with current system millis. I'm going to receive it as a parameter. Someone else is going to give me the time. So I'll evaluate that. And then as I move further up the stack, my generate random add impression and generate click functions will also receive the time from somewhere else. We want to make it somebody else's problem at the edge of the system to provide time to us, so that that messiness doesn't kind of pervade the rest of the stack. And so I'll run these two, evaluate these two functions. Ditto with my top level generate data function. It will receive time as a key of a map. And then same with the actual generation function. Instead of receiving the timestamp, what we're going to do is receive a function that produces the current time. So that function is called nowFun. And whenever I invoke it, it tells me what is the current time. And so I go and I run my data generator and then recur and get the current time again. And so the magic here is actually just having a piece of outside state. There are many ways you could do this. I tried to keep it really simple for this talk. I still have my random seed. I rebind my random object. And I have a mutable variable called now. I just set it to 0 because it's really simple to follow. And then I pass in a function that swaps the current timestamp and just increments it by 1. And so from the perspective of my generators, time is just going from 0 to 1 to 2 every time I invoke it, which is amazing for writing unit tests. It's just so much simpler to look at these things and being able to reason about them. If I run this, I won't actually see the functions like the timestamps 0, 1, 2, and 3. I'll actually see timestamps that look like -435, 494, whatever. And the reason is that I had my deterministically random functions offset the time, into the past or into the future. But it doesn't have to be 0. It could be anything that makes sense for your system. But if I run this over and over, we're going to still see the same timestamps. We now have deterministic time on top of deterministic randomness, and those compose. And so I always see the last timestamp at -435. So really useful being able to do that. So to go to the last two segments of kind of the pyramid of doing this well, I want to talk about how you do correlated data in a way that is fast and performant. So when I introduced this, I mentioned it's actually quite important to be able to have add IDs that are occasionally matching in the add impression and the click. Otherwise, the critical code will never get triggered, and the business logic doesn't actually run. And so we want these things to sometimes be the same. Well, how do you do that? When you build a synthetic data generator, you actually have to remember the data that you're producing for these add impressions so that you can occasionally go grab one of those IDs and reuse it for a click. This is actually harder to do than it sounds. This ends up being a problem in data structures where you need to index the data as you go, and you need kind of a funny assortment of characteristics in a data structure. It needs to be sorted because you can't retain data forever, otherwise you just run out of memory. And so because it's sorted, you need fast inserts at the tail, fast deletes at the head, because you want to probably delete data that is older and just retain the newer stuff. You want fast random access, because you don't want to always grab the last add. You want to grab whatever adds that you have on board. And then you want to have fast set operations. There's many instances, a little bit outside the scope of this talk, where you'd want to compare what is the set of all add IDs I've ever generated and the set of add IDs I have in other functions, and figure out what's the difference, what's the intersection. And so this is sort of like a funny list of characteristics to get out of a data structure. I've searched high and low for the right things. I change this all the time because it's actually the most performance-sensitive part of ShadowTraffic, so take this for a grain of salt when you see it. But comparing the performance of Java, Clojure, Scala against other off-the-shelf libraries, a library called Bifurcant actually performs incredibly well. It's a set of persistent data structures for Java, and it turns out an int map is actually an incredible data structure for doing this. The int keys are sortable. Because it's a map, it supports set operations. It has fast lookups, again, because it's just a hash map. And as you add more and more elements, these things actually can dramatically outperform the standard libraries on other programming languages on the JVM. And so, again, fast lookups on fast random lookups on the keys. Map difference is basically stable because it's an int map. All it's doing is adding contiguous keys. And the same with intersection. These things perform really, really well. And so this is the biggest knob in doing high performance when you do multiple data sets, is just making sure you're indexing the data in the right way. And so these things are worth the hunt. They are all the difference in making high performance for systems or not. So I'm going to show just a little bit about how this works. If I go over here. I'm going to go ahead and modify my running example. So I'm going to initialize an atom, which is like a variable, with 2 of these int maps from Bifurcan, one for the add impressions and one for the clicks. And I'm going to declare a dynamic object for these histories. And so I have both of them, and I can rebind them as I like. And I add a new function called lookup. So I take a topic that I want to get historical data for. I go and I get data from the history. I look at the keys. I use drandint. This is a great example where you have to be really, really careful every time you use a random function to just grab a random element from that map. And then I just use env to access that stable key. And you go ahead and return it. And all I have to do then is update my definition of what it means to generate a click. Instead of grabbing a random add ID like I did before, I'm going to call lookup on the add impressions collection, grab a random add ID, and then use that so that they always remain correlated. And the rest of this remains the same. I use my stable random time, random URL, random UID functions, and then just a little bit of plumbing to actually make this all work. Whenever I produce an event, I actually want to save it to this history. So I swap my histories. I look at the topic that it belongs as part of, I put it into the old history, and then I just reassociate it so that it basically tracks it over time. And on top of that, all I gotta do now is update my execute side effects function. So I send the data to Kafka, and then I index it into memory. You wanna do it in that order, because if you don't, you can have a missed send, and you can end up accessing data that never actually made its way to Kafka, and that will leave you scratching your head. And then lastly, this is the last little bit of code. I'm gonna augment my random seed. I go ahead and I initialize my random object again, initialize my histories, set my timestamp to 0 and pass in my timestamp function again. And now, if everything goes well, I have fully deterministic data with predictable timestamps. And so notice I'm running this over and over again. The timestamp at the bottom in the last event is always negative 122. The add ID is always the same, D372. If I look for the add impression on the first click, it's BA419 that actually matches my first add impression. So these are correlated. And now I can run this as much as I want. This is great for testing. This is great for reasoning about how your system will behave. And these are just kind of the bones of what you would do for your own system if you wanted to kind of replicate these techniques. The last thing I wanted to talk about, I don't have any code associated with this because it's somewhat of a complicated topic. I mentioned that the goal is to generate data like this, which is what we did, but to do it with a DSL that's very high level and dynamic. And we didn't quite do that. We stopped with like writing code to actually support each of these functions. I want to talk a little bit about how this works. It's the subject of an entire talk of itself, but I wanted to give you kind of like the theme of how it works. So the way that this works is you want to actually take a data DSL like this, and you want to deconstruct it into a tree. This is actually kind of like a programming language problem where you take this, you arrange it as an abstract syntax tree, and you deconstruct it. We take our generated event, we arrange it into key and value, and then we go through each of the leaves in that data structure, and we look for maps that have underscore gen, and those are functions that we're going to look for, and we do a two-stage pass. Number one, we want to do a bottoms-up compilation, looking for any of these functions and compile code inline. And then second, we want to do a repeated top-down execution and actually go and find those functions and execute them and reinsert code in those spots. This is kind of a high-level, gloss over description of how it works, but it's very similar to a compiler and an AST, and this ends up being an incredibly performant way, very similar to doing correlated data. You kind of have to get this hot path code just right to be able to generate data quite fast, and this is the approach that I've taken that's worked out pretty well, so I kind of recommend it. And this does it. These are the techniques that have proven to be very important over time, and to be able to produce hundreds of thousands of messages to Kafka a second that are of the shape that you want, deterministic, easy to work with. And yeah, thanks for coming to my talk.